In this video, we're looking at a CRC, or a cyclic redundancy check. And basically, CRCs, which are also known as polynomial code checksums, they've been around since the 60s. So Wesley Peterson, 1961, when these originated. And in many ways, they're quite similar to an LRC. Essentially, we've got some sort of error detection code that we append as a checksum to the end of a block of data. So we have a whole block of data. At the end of it, we compute some sort of a checksum and we put it in there, we transmit that. We perform the same operation at the sender and the receiver, and we compare them against each other. One of the problems with the LRC, though, is if data is sent out of order, it'll generate the same checksum. So if you send ABC and send CBA and calculate an LRC for either one of those, you'll get the same LRC. Whereas with CRC, it's a lot more robust. It will do single bit errors really well. But if things are out of order, it'll compute that well as well and check whether there's been errors that have occurred, things out of order, things missing, more robust than the LRC. It's also reversible, so it's not something we use for cryptography or anything like that, but a really nice check for and robust check for looking if there's errors that have occurred. Now, CRCs are really commonly in use. Lots of places we find them, for example, in the Ethernet protocols, USB protocols, GSM protocols, the serial ATA protocols, in image files like PNG files, in Bluetooth, very, very widely used. And CRCs are probably one of the most widely used checksums around. It's something that we compute at both ends and very accurate, and there's a whole bunch of different standards, and those standards specify how long the checksum is going to be and what polynomial we're going to actually choose to actually encode that checksum. So some of the common ones are, for example, CRC 8, 1632, and 64. But there's quite a few others, and there's quite a few different varieties in each of these ones as well. So, question is how they work. Essentially what we're doing when we're doing checksums is we're doing polynomial division. But we're not doing polynomial division in the traditional sense in dividing by a big number, because division in microcontroller land is a very expensive operation. So we've got some shortcuts how we actually do that division. But what we have, we select some sort of a polynomial, both at the sender and receiver once again, and we divide each chunk of our data by that polynomial. And we do it by using XORs and some bit shifting along. Now we've got a number of different polynomials. For example, CRC 16, the standard one we've got there, x to the power of 16 plus x to the power of 15 plus x to the power of 2 plus 1, for example. CRC 32 is a whole lot longer, a whole lot more digits in our polynomial that we have there. So we need to choose which polynomial we're going to use. It's really great to be able to go through a work example on these sort of things. So let's go through a work example, but let's cut it right down and we'll use CRC 5 because it's a much shorter polynomial. It's a lot easier to see what's going on compared to if we extended this out to CRC 32, for example. Now what we need to do is work out, based on our polynomial, how we encode this in binary. And we encode this as binary coefficients to our polynomial. So each of those terms that we have there, when we express CRC 5 polynomial, x to the power of 5 plus x to the power of 2 plus x to the power of plus 1, with each of our coefficients, which are shown in red, it's either going to be 1 if it's actually listed in our polynomial, or 0 because anything multiplied by 0 is 0 if it's not listed within our polynomial. Now the basic steps when we're doing our CRC computation is we line up our most significant bit of our polynomial with the most significant one in the data that we're using. We pad data to the length of the CRC, so in this case we do it 1 less than the length of the CRCs. We perform an XOR and then we shift our polynomial along and perform another XOR when we shift it and line it up with the next 1 in that case. So let's see how it looks. So what we have here, we see our chunk of data at the top there. And what we want to do is line our CRC, CRC 5 in this case, with the first one in that chunk of data. So we've lined them up and we perform the XOR. So 1 and 1 XOR 1 is 0, and we perform the XOR for all those other bits. And then we've generated a new chunk of data that we've got there. Once again, we line our polynomial up with the most significant one in our new chunk of data. So in this case, we just shift it by 1. We perform the same XOR operation, and that will give us a new value. Now this time, our top 2 bits there, or our top 3 bits in fact, are all zeros. So this time we don't shift by 1 because that would line us up with a 0 again. We shift it by 2. And once we've shifted it by 2, we do that operation again, and we do it again, and we do it again, and we do it again, until we can't shift it anymore because our polynomial is larger than the remainder value that we got. That remainder value is our remainder. It's our CRC, and that's what we use to send in our checksum or check our checksum against at the receiver end.